also it's given, we have to find derivative at the 1 0. Okay. So component, if you write the component of A, one is x plus y, another component is x2, x into y. Okay. F is your f1 comma f2. So calculate partial derivative of f1 with respect to x, which is 1, even at the point 1 0. We have to calculate it at the point 1 0. And partial derivative of f1 with respect to y at the point 1 0 is again 1. Partial derivative of f2 with respect to x at the point 1 0 is, so it will be y and it will be 0. And partial derivative of f2 at the point y, it will be x, so value will be 1 at the point 1 0. Correct. So what will be the f dash 1 0? So f dash 1 0 will just calculate the matrix of f of 1 0, f dash 1 0. It will be this quantity first, so 1, then 0, then 1, then 1. And it's invertible at that point. If you calculate the derivative is non-zero, so it's an invertible function. F dash 1 0 is invertible. So that's how you get your derivative at a point. Fine. So simple. Okay. Similar to this, question number 30. So find the derivative at the point 0, 1, 3, 2, 7. Can you do it type? Just a simple practice. F is given as f1, f2, and components are given by the formula. Find the derivative at that point. So, what will be the order of the matrix? 2 cross 3 or 5. 2 cross 5. Who got the answers? Question question number 30. The first row is correct. Second, minus 6 0 or 1? Minus 6 1 2 0 minus 1. That will be the answer. Okay. So first row will be 2 3 1 minus 4 0. Second row will be minus 6 1 2 0 minus 1. So I am not doing it. I hope that you can do it. Just using partial derivative, you have to do that. Okay. Question number 31. So it's again the same function we considered in question number 29. Now verify the following statement. F is not differentiable at the point 0 0. Is it correct statement? Is it correct? No, it's not correct. Right. Because at any point we have calculated the matrix. We can consider the component function f1 of x plus y and f2 of x equals to xy. So both are polynomial in xy, so partial derivative will exist at the point 0 0. So f is differentiable at the point 0 0, obviously. Now it's not there in this question, but can you tell me whether f the 0 0 is an invertible function or not? F the 0 0 invertible or not invertible? F the 0 0. Will it be an invertible? No, it will be not invertible. What will be the matrix? So you see that we have calculated for 1 0 it is 1 1 0 1, and for 0 0 it will be 1 1 0 0. So that will be not an invertible matrix. Okay. So first statement is incorrect statement. F is differentiable at the point 0 0, but accepting you can say that f the 0 0 is not an invertible matrix. Okay, the derivative of f is invertible except on the set xy comma 12. So again calculate, is it correct statement? Derivative of f is invertible except on the set that is the line y equals to x. Is the correct statement or false? For any point xy, calculate the derivative. What will be the derivative? So question number 30. So if we calculate any point, the derivative will be 1 1 will be there, correct? First row will be 1 1, but second row it will be 0. Not 0 0. xy. No, first yeah, it will be yx. Now when it will be invertible, if we calculate the derivative of this matrix, if x equals to y. If x not equals to y, it will be invertible. So that statement is no, it's correct. Derivative of x is invertible except on that set. So when x equals to y, it's not invertible, otherwise it is invertible. So statement B is a correct statement. Fine. The inverse image of each point in R2 has at most 2 elements. Inverse image of each point in R2 has at most 2 elements. It's not related to derivative, but just simple thing. Inverse image of R2 means what? Consider any point A and B. So what we could do, it's a correct statement or false? So inverse image means what? You have to find x. Let's say we consider a point AB. Okay. Each point, let's say point AB, then you have x plus y will be A and xy will be B. Okay. So that means what? If you solve this equation, you will have at most 2 roots. So therefore, that is the correct statement. Inverse image of each point has at most 2 elements. Okay, if you are not getting it, let's calculate. So let's say AB belongs to R2. Okay. Then we want to find XY such that this will be A comma B. But f of xy is x plus y into xy, which is a plus b. Sorry, a comma b. This implies that x plus y equals to a and xy equals to b. So what is y? So x into a minus x will be b. A minus x. So it's a quadratic equation in x. So you will have at most 2 different roots, and therefore you have at most 2 points. Next question was, is this surjective? So that means for all A and B will you get the solution? So for which A, B will not get the solution? 0, 0 or x. Okay, is it? If you get the 0, 0, you have 0, 0 maps to 0, 0. Obviously it has the image. Either you can solve that equation and say that for where you are getting complex roots. So what about if I consider the point 1 comma 0? So let's x plus y equals to 1, xy equals to 0. Okay, so it will be x into 1 minus x equals to 0. So x equals to 0, x equals to 1. This has a solution. But if we consider x plus y equals to 0, but x into y equals to 1, then x into minus x to 1 and you have minus 1. So you have no solution. So 0, 1 has no pre-image. Okay. So this is another way to check, but you can check directly whether when this equation has solution or not. So it is not a surjective map because the point 0, 1 has no pre-image. Here. So AB is correct, but CD is false. CD are false in this case. Okay. Question number 32. Suppose AB is a continuous mapping on AB for Z equals to f of b minus f of a. Define phi of t as Z into ft, means it's the inner product of the vector Z and ft. Okay, in Rn, so that phi is a continuous mapping. So in general, let's say we have 2 continuous functions g and t. So that, so I will, instead of solving this, you can solve this more general version. Try to solve this one. Let's say phi of t is the inner product of gt dot ft. Both f and g are continuous functions. Okay. So we have to show that phi is a continuous function. So t belongs to closed and bounded interval AB. So dot product means you can also write in this following way: g of t, comma f of t. Just the inner product. How to show? So calculate phi of x plus or t plus h minus phi of t. Then take the limit h tends to 0. So what is phi of t plus h minus phi of t? It is g of t plus h, comma f of t plus h minus f of t, comma g of t. So what is the value we are getting? G of t plus h. Sorry, we put, yeah, it will be in reverse. G g of t comma phi of f of t. So minus g of t f of t plus h minus f of t. Then what shall we do? H into no, not g dash. It's only given that f and g are continuous functions. We don't know whether derivative exists or not. So what is about the mode of phi of t plus h minus phi of t? Mode means norm in this case, Rn. Yeah, which inequality? Mode of the component into mode of second component. Swatch inequality. Correct. So this will be g of t plus h minus g of t f of t plus h minus f of t, and then by Swatch inequality g of t into f of t plus h minus f of t, and then because they are continuous you can make in such a way that it will be less than itself. So done. So therefore it will be a continuous function. Is it clear? Just using Swatch inequalities in this case we got the solution. In the question, g of t is nothing but a constant. So constant function. So it's true in general. If f and g both are continuous functions. Okay. Question number 33, we have to calculate the derivative of again inner product. So f is differentiable of function of ab into Rn. So again I will ask you to show this. F and g both are differentiable functions. Is it 32 correct? So let's say our phi of t is defined as f of t or whatever we retain as g of t comma f of t. So that derivative t, obviously assume that a derivative of f and g exists. It is same as g dash t comma f of t plus g of t comma try to show. Okay, you may try later the similar type of thing. What we did for the continuity case, you have to do it for the same type of thing because you have to solve some other good question at the end. So it's just a regular calculation using. So you have to attain. You have to use the property that inner product is inner product is a continuous function. Then you get 34. Suppose f is a continuous mapping of AB into Rn and f is differentiable in AB so that there exists an x so that there exists an x in AB such that mod of f of b minus f of a, it's like that. It's almost mean value theorem, but because it's we are considering a mapping, vector value mapping, we have this following type of thing: f of b minus f of a less than equals to f plus x b minus a. continuous mapping of AB into R, if is differentiable in AB so that there exists an X such that f of B minus f of A less than or equals to this. Okay, hence is that consider phi of t as j into f of t, like what we did in the last two problems, 32 or 33. So look over here, phi is a mapping from where to where? R to R. So you can use mean value theorem for phi. Okay, use mean value theorem for phi, try to get the solution. Okay, let me write down the question first. Over here. What is given? F is a function from Rn and it is differentiable function. Okay, differentiable on open interval AB. So what you have to show? Mod of f of A, f of B less than equals to what it is? Mod A plus X into mod of B minus A for some X belongs to open interval AB.
So a mod means
A mod in Rn. F of B minus f of A is a mod in Rn. Mod of f plus x is a mod of the operator. Okay. And then mod of B minus A means just a number. So it's a just B minus A.
mod of the operator means the same as
Okay, let me define mod of the operator. So if we have a mapping from Rn to Rn, okay, so we are defining mod of A, I mean norm of A is equal to suprema mod of x less than equals to 1 mod of fx by mod of x. That's how, okay, in place of a, we have a. But don't bother with the mod of the operator in this case because you can think because it's a real single value function, vector value function of single variable, this mod of this x will be a vector of Rn. Okay, so do not bother with that. Okay, so what I said, so put z equals to f of b minus f of a. Fine. And define a function phi of t is j dot f of t. So t belongs to this. So if you use the last two exercise, then phi of t is continuous on closed and bounded interval AB and derivative of phi exists on open interval AB. So using last two exercise, one data we have phi is continuous on closed and bounded interval AB. Second thing is that phi is differentiable on open interval AB. Okay. Then by because phi is a real valued function, actually real function, then there exists an x belongs to open interval AB. What will happen such that phi dash t, it's not phi dash t, the phi of b minus phi of a is equals to phi dash of x into b minus a. Right. That was the theorem. Phi of b minus phi of a is phi dash x into b minus. MBT, fine. Means that the theorem of real function. Now what is phi dash x? Look at that exercise. Phi dash t is j dot f dash t. So this will be j dot f dash x into b minus a. So this is inner product over there. So this is, but let's say this is 1. But what is phi of b minus phi of a? Phi of t is j dot f of t. So this is nothing but j dot f of b minus. Okay, if you are not comfortable with this, write that j dot comma f of it. So what is the value we are getting? Cancelling out. This. Okay. Yeah. Yes, yes, correct. This is j, mod of j whole square. Yes. Okay, so you have to consider one by one. 4 terms will come there. Okay, so here is some issue is there. So just change it because it will be not phi of t plus h minus phi of g of t. So you have to mold it little bit. So 4 terms will be there. But the answer will be same. That phi will be a continuous function. So phi of b minus phi of a will be mod of j whole square. So this is 1, 2. Now if you 1 and 2, from 1 and 2 what we are getting? Sorry. In 1 we got phi of b minus phi of a as j dot f dash x b minus a. This is same as phi of b minus phi of a. And here we got phi of b minus phi of a is mod of j square. So we have mod of j whole square is equals to a dot fx into b minus a. Okay, actually we might not need this, but anyhow we get this information. Now we have to calculate phi of b minus phi of a. If we calculate the mod of it, so
So it's less than or equal to mod z.
Yeah, so this will take us mod of j dot f dash x into b minus a, correct? And this will be less than equals to fx. No, this will be equal till now. And then again Schwarz inequality will give us mod of j into f dash x into b minus a, because mod of b is this. Okay. And this side is nothing but mod of j. Is it clear to this one? We are taking mod of f of phi of p minus phi of a is this one. So mod of this is a real number. So this is a real number, that's a real number. So mod of a into mod of b. Now using Schwarz inequality, so inner product of z comma fx. We write as inner product. So this will be mod of z into mod of f plus x. Okay, now this side is nothing but mod of j whole square. So mod of j cancel out, we have mod of j less than equals to f plus x into b minus a. But what is mod of j? So this implied as mod of f of b minus f of a, because j is nothing but f of b minus f of a. We have f plus x into b minus a. Okay, that's how we got the. Okay.
So can write this equal variable. The f of x is equals to in terms of what 1 of x, 2 of x, dash dash.
Okay.
Now, that's why is that differential. Because f is equal to f by z. Now we can apply any value there.
Yes, for each quantity we can apply. Yes, yes.
For each value we get one xi. Now we substitute back.
It will be summation upon
Of b minus f of by b minus a. We get 1 by b minus f1 of b minus f1 of a, comma f2 of b minus f2 of a dash f1 of b minus f2. So that is equals to 1 by b minus f1 dash of x1, comma f2 dash of x1 dash of x1 dash of x1. Now we have to change the value of x in xi so that that modulus will be maximum. So f is less than or equals to f dash of x modulus of f dash of x.
maximum where you are taking.
We get f of b minus.
So for each component you are using mean value.
Yes.
Okay. Then what you are writing f of b minus f of a is same as that f1 of b minus f1 of a for each component. Let's say fi of b minus f of a. So in place of fi of b minus f over a, you are putting fi zeta. Zeta. Now let's say for f1 you have zeta 1, but f2 you have zeta 2. Then you will not going to get the supremum of something. Okay, so in that case you are taking maximum of all the derivatives.
We are choosing the value of zeta. So this is where the modulus will be maximum. Zeta is equal to zeta because that modulus will be maximum.
So modulus you are ultimately what will be, you will put the zeta 1, let's say for f1 you have zeta 1. So f1 that zeta, f2 that zeta, f3 that zeta. So we were taking the maximum of all those numbers. But is it possible to get a number zeta such that the derivative of the function at that point, the mod value of the derivative will be zeta is we have to think about it that way. So whether we will get a zeta such that f plus zeta, mod of f plus zeta is greater than equals to that maximum of all those numbers. Whether that zeta exists or not.
So zeta will be equals to zeta because only finitely many zeta.
Finitely many here. So but even that finite numbers is called fi's. But for f plus zeta, that's another totally different number. Now you were comparing numbers, but the comparing mod value of f and the mod of all those numbers. So it's actually that the zeta, you can compare the numbers, but zeta, how you get the zeta, that's not correct. I am not sure. I think you are also saying the same thing. So you are calculating maximum of f1 dash of zeta 1, f2 dash of zeta 2. Let's say mod.
I'm not comparing individual ones.
Then what has come?
So, modulus of the first modulus of first dash of x zeta
Zeta 1.
dash comma two dash of zeta dash dash of zeta. This value less than or equal to.
This value is equals to.
So for some zeta, this will the entire this will attain maximum.
Okay, it will attain some maximum value.
So this will be less than or equals to modulus of f1 dash of zeta, that zeta, f2 dash of zeta, dash the f1 dash of zeta.
Okay. So ultimately this will be the maximum, then you take the sum of it, right? So if it is maximum is this obviously it will be less than equals to sum. Okay, whatever is the maximum of this, how it will be maximum? To be plus or something like that.
See, there are finitely many zeta.
Okay, anyhow, this is mod value, what will be this value? This is the square root of all these numbers, sum of, so this will be nothing but square root of f1 dash zeta 1 square, and then you have fn dash zeta n square. This is a definite number, okay.
For some zeta is equals to zeta, that value will be maximum.
Yeah, some zeta I will be there for which this value
Zeta is equals to zeta I.
zeta equals to zeta I will take for which
Root of f1 dash of zeta.
f1 dash of zeta
Square of zeta plus f2 dash square of zeta. Dash f2 dash square of zeta. This will be maximum.
okay.
Now I am choosing that zeta.
Yeah, I think then it will work. Yeah, I think then it will work because it will be the mod of theta. Yes, I think it is working. Yeah, it is working. Looks like it is working. Yeah, you can approach this too, I guess so. But please verify. Is whether it gets any flaw. Yeah, like there will be one zeta for which it will be less than or equals to their all the sum. I'm not sure. Just a minute. Again, there will be one zeta rn. So let's say first zeta k, that fk zeta k is maximum of all these numbers. But f1 of zeta k, whether it is greater than f1 of zeta 1 square or not, how will it? You cannot choose that way. Sum is maximum. But that what will be that zeta will be inside of open interval area or not? Will grant it.
So every zeta is inside a.
Every zeta is in Nobel, so that means your zeta is one of zeta is. Now in that particular point, whether the f1 of zeta 1 is okay. So what your zeta is for which all these quantities greater than. So for this zeta k, you are saying this value is greater than equals to maximum of f1 zeta 1, f2 zeta 2, fm zeta n, correct? Is it what you are saying? What are you saying here?
The sum f I dash of zeta j, the square root, this
Square.
Square root
Sum.
of and this is square. You consider this sum. So this is since there are finitely many zeta i's, but for different combinations of this one, this will attain a maximum value for some zeta j.
So you are taking summation both in I and j, or your I and j is same?
I'm choosing the zeta j now, fixing the zeta j. Now varying I.
Okay.
Now take its maximum. For some zeta j, it will attain maximum.
Okay. So for each, so like for f1 zeta 1 you are calculating, so like you are calculating f1 dash zeta 1 square plus f2 dash zeta 1 square,
Yes.
fm dash zeta n square, okay. And then again for zeta 2 you are calculating
Yes.
all those sums. For all then zeta 3 you are calculating all those sums. Obviously then there will be a maximum.
So this mod will be less than or this sum will be less than or equals to that one.
Yes, because will that be that combination, but that combination is not considering that sum. Like f1 zeta 1, f2 zeta 2 in your sum, there will be no such thing as, because you are fixing this, so there will be no quantity like f1 dash zeta 1 square plus f2 dash zeta 2 square, f1 dash zeta square. These are the totally different sets of sum. So then we cannot say like. Okay, it's a good approach. I mean, maybe we have to think a little bit. It might possible. Thanks. You got it. Ultimately, what is the problem? It's calculating all this thing, but that quantity is not coming in this collection.
Even in the previous one, first way, that's for example, comma f dash.
Yes.
So the z is a vector, f dash is a
J is a vector f of b minus f of a. It's a fixed vector.
it is a vector. Now f dash is a like a base
More a vector x.
the first line.
This one.
Yeah, whole line. We will call it z comma f dash. So
Yes.
that is a linear transformation.
This will be a number, real number. Inner product this will be a little. It's the inner product of z comma f dash.
Between two vectors, z is a vector, but f dash
Z is a vector, f dash x is a vector. Because derivative is a vector of Rn. Z is a vector of Rn, f dash x is a vector of Rn.
you add an element, then it will become.
No, we're not getting it. When we discuss linear transformation, here linear transformation is a constant linear transformation. When you are taking single value function from R to Rn, your linear transformation will be just multiplied by the vector itself. So R1 to Rn, that linear transformation f plus x is a linear transformation, but it is also a vector in this case. When you have Rn, n is greater than 1, then you have a linear transformation. It might not, it will be not vector. But when you have Rn to Rn, so if we have this space Rn to Rn is isomorphic to Rn. Okay, this space is isomorphic to Rn. So although we are considering f plus x as a linear transformation, but here we have just need to consider it is a vector. Okay. Fine. Okay, 34. Go for question number 34. So 34 is basically generalized version of question number 33. So 33 you have single value function from AB to Rn. Okay. Where is 34? No, 34 will be correct. 35. Sorry, 35. So it was from closed interval AB to Rn. So single value function. Now we have multivariable function. So now also in place of closed interval we have just an open set E to Rn, and F is differentiable at actually in E, and there is a number m such that f dash x less than equals to m is given. Then show that mod of f of b minus f of a or f of a minus does not matter less than equals to m into b minus a. So it's again generalized version of mean value theorem, but here now from Rn to Rn, or like an open set of Rn to Rn. Okay. You have to use question number 34 to solve question number 35. So you see that to solve question number 34, we use the mean value theorem or real value function of real variable. Now to solve question number 35, we have to use the vector value function of real variable. Just one single real variable. So how to do it? This one. So we have a function. How to get a function? It's a given that is a convex set. That's the important part of the story. E is a convex set of Rn to Rn. Okay. Why we are doing it? Because the question number 36 is our ultimate goal. When we go to the question number 36, that will be our ultimate goal. But actually, to solve that question, we need all these steps. Okay. That's how. That's why I make this. Okay. Now, how to do it? So we have a convex function. So idea is that suppose X maps a convex set E of Rn. F is differentiable at or E, and then there is a number m such that the derivative is given as bounded. Okay. So for all x, it is bounded. Then for whatever a b will choose, mod of f of a minus f of b less than equals to b minus a. So now we need to get a function from AB to Rn type of thing. So what we'll do, define a new function. Question number 35, correct. Define phi of t as 1 minus t a plus t into b 0 less than equals to t less than equals to 1. Now we have a function from Rn to Rn. Sorry, R2. So phi is your function from and it's a differentiable function. So it's again we see that 1 minus ta plus t comma b is obviously a element of Rn. Oh no, it's an element of E. Okay, this is a function of Rn. Okay, that's my mistake. Actually, it's a mapping E. Okay, let me write in the it's Rn. But this phi of t belongs to E since E is convex. Because E is convex and 1 minus Ta plus T minus B is a just line segment joining the vectors A and B. Okay. Now define a new function g of t. Okay, so this is a function, we need a function from Rn. So let me define a function g of t as, okay, so I will change the name because I want to use as what we did before. So I write this as a gamma of t, this is gamma of t, and phi from AB to, Actually, I made a mistake, I guess. No, it's fine, correct? AB2 Rm by I of t as A of gamma of t. Is it correct, ma'am? A 0 less than equals to, okay, A B in place of AB. E Rm. Oh, it will be 0. That's why I'm changing all this. This is in 0, 1. Correct? Now, to is it now correct? It's just little bit tricky. So gamma of t is a mapping from 0, 1 to R. Fine. And because A is convex, gamma of t belongs to E. And phi is a mapping now from 0, 1 to Rn. And phi is defined as phi of t is gamma of f of gamma of t. This is now mapping from 0, 1 to Rn. Fine. Is it clear now? If it is clear, then by question number 34, question 34, mod of phi 1 minus phi of 0 will be less than equals to phi dash x into 1 minus 0 for some x belongs to 0, 1. Fine. By question number 34. So now what is phi of 1? Phi of 1 is f of gamma of 1. F of gamma of 1 is f of b. So this implies that mod of f of b minus f of 0 is phi of 0 is f of gamma of 0. Gamma of 0 is a. So gamma of 0 means that means f of x. This is less than equals to mod of phi dash x. But what is mod of phi dash x? By chain rule, f dash gamma t or gamma dash x into gamma dash x. Okay. So this is less than equals to f dash gamma of x. So this is now your linear operator norm into gamma dash x. Now what is gamma dash x? It's nothing but gamma dash t will be nothing but minus a plus b, so b minus a, and f dash gamma x is given f dash x is less than equals to m for all x. So this will be less than equals to m into b minus a. So we prove it will be mod of b minus. Fine. That's how we proved our rate. Gamma dash x, so you can write over here gamma dash t is nothing but b minus x. And be careful, this norm I used over here is a norm of the operator Rn to Rn, norm of the operator. Fine.
convex that convex.
Yeah, for convexity we need this one. Otherwise, gamma t cannot be in E. Okay. So to get that it is in E, we need to consider E as a convex set. Okay. Now, the final thing of this idea is question number 36. Not the final question, but final of all this. Suppose F maps a convex set, open set E of Rn into Rn, it is differentiable. I don't know why adding it every time. So in E such that f dash x is 0 for all x belongs to E, then show that f is a constant on E. So f dash is a 0 operator, f dash x, then show that f is a constant on E. So how will we get the constant? Using question number 35, m is 0. If your m is 0, then mod of f of b minus f of b, a will be 0. So whatever a b you choose, f of b will be f of a, so a is a constant function. Is it clear to everyone? So in the last problem, choose m equals to 0, then whatever a b you have, f of b minus f of a, mod of that will be less than equals to 0. That means mod of f of b minus f of a is 0. Therefore, f of b same as f of a. Now, because this is true for every pair of AB, f should be a constant function. So, what you learn, like for the function of real value function of single variable, if derivative of a function is 0, then function becomes, so if function is a derivative on open interval is 0, then or in any convex set it is 0, then function is a constant function. So, similarly over here, if we have a vector value function of several variables, and on a convex set, if the derivative is 0, the function should be a constant function.
What is non-convex?
The non-convexity obviously define a constant function which will be 0. I mean, for a non-convex set, you can define a function whose derivative can be 0. Now, we cannot necessarily say that it will be a constant function. So you can take, we'll discuss in the next year, question number 38. Okay, we'll discuss the same thing, what he said. So he is asking. Suppose we have know that f dash x is 0 on an open set. Can we say that the set should be a convex set? Okay. Or like if it is something else, if it is not convex, what will happen? So we'll go to this problem. Okay, but for question number 37 first. Let f from Rn to Rn be a differentiable function. It might not be a linear one, but a differentiable function. Verify the following statements. Derivative of f at 0, is it a 0 operator? Need not be. For example, consider f as a just a matrix. So then at the 0 point, it will be the matrix itself, and that matrix is non-zero matrix. Okay, so we got it. So 37a, consider a, so it be any differentiable function. So consider an m by n matrix, non-zero matrix. Then the derivative at the point 0 will be the matrix itself, and then matrix is a non-zero matrix, so it's not going to be a zero matrix. So this is a false statement. Question number A is a false statement. Question number B, if for some x, so dfx u is 0 for all u, so it's a 0 operator, so dfx is a 0 operator, and for some x, then can we say that is it necessary that x should be a constant? No. What is an example?
X, Y, Y, X.
No, df of x, df of x should be a constant matrix. At x, when you are operating, df of x is a matrix. Then you are operating on Q.
You can take df of 0, u.
So actually, you can use the last example as well. Last example, consider again non-zero matrix. Okay. So for whatever x you will choose, that will be, oh no, it's given that it will be 0 for all u. It's given that it is 0 for all u and for some x. So can we say that x should be a constant function? So yeah, it's similar to option A, but just little bit carefully you have to make the statement. Okay, let's take. Okay, one simple thing you can think about, just take a f of x equals to x. No, f of x equals to x will give.
You take a function from 1 to 2, that its derived matrix is of the form x y by x.
We don't need derivative. Okay, let's see what we have. We have f of x of u equals to 0. It is true for all u belongs to Rn, but some x belongs to Rn. Okay. So be careful. This is your matrix from Rn to Rn. Okay. Let's consider a function, real function. What will happen? So can we have a point where the derivative is 0? Obviously we can have. Like consider f of x equals to x squared, this function. So derivative at a point is 2x. Okay. So derivative x when x is 0, it is 0. So but it is not a constant function. Got it? So think that f is a mapping from your aim is now 1. F is a mapping from R1 to R1 defined by x maps to x square. Okay. Now what is dfx? So x I am taking x as for some x, so I am taking x as 0. Then derivative at the point 0 is 0. Now 0, think 0 as a linear operator in R1. Now whatever u will give, 0 of u will be obviously 0. Okay, but f is a non-constant function. This is clear. I think you were also saying the similar thing. So this proves that, is it clear to everyone? It's a little bit hazy because we are moving from derivative of point to a linear operator and all sort of thing. So this is how why B is false again. What about the third one? Third one is true. Why? Don't say you, someone else. Why third one is true? df of x of u is 0 for all u and all x. Then it will imply that it is a constant. Yes, it is nothing but the question number 36. Your E is now the whole space. So it's saying that derivative at each point is a 0 operator. If you forget about this, U, then dfx equals to 0 is this implies that dfx is a 0 operator. So derivative at each point x is now 0. When we write f dash x is 0 means what? This operator acting on all the values of u will give you the 0. So therefore dfx of u 0 means this is nothing but that one, and if we know that if f dash is 0 then it should be a constant function. Okay. So therefore question number C is a correct statement. Okay. Clear? Question number D. If f is a non-constant function, then dfx is a one-to-one function for some x. It will be one-to-one function for some x. If f is a non-constant function, then some x will exist for which the operator will be 1 to 1. Is this true? Think about the matrix. What is, if I consider a non-invertible matrix? That means function is not 1 1. Okay. Okay. So then what? So I am considering a matrix. Then that's a non-constant matrix. Okay. And okay, so no, constant matrix, it is becoming constant. No, each point of x you will getting the same value. So f is not a constant function. Yeah, you can have a function. You need to get a function first. What is that function you get for which you have a matrix which is non-invertible? So if we have f of x plus f of x comma y, let's say x plus y comma or anything. Let's say 0. Okay. What is the matrix of the function del? Okay, f1 of x comma y is your x plus y. f2 of x comma y is 0. Del f1 del x is 1. Del f2 del y is 5. Del x is 0. Del f1 del y is 1. Del f2 del y is 0. So whatever x you have, f dash of xy, whatever point you have, this vector, this will give you the matrix 1 0 1 0. That's a non-invertible matrix. So whatever you will have, so it's not true basically. So this is a non-constant function. You can clearly see that non-constant function. But what is going on? D of fx is 1 to 1 for some x. No, for all x, you get the same matrix 1 1 0 0, which is not an invertible matrix. So yes, any non-zero, you have to just find a proper function f for which you get that matrix. Yeah, so the function you will get that same function linear. Yes. So option D is also incorrect. So only option C is correct in this case. Okay. Yeah. Okay. Now question number 38. Try to solve question number 38. E be an open subset and we have a differentiable function such that f plus x is 0 for all x, like any open set. Then verify the following statement. F must be a constant function. No. What is an example? No, derivative should be 0. Previous one derivative is not a 0. Previous one derivative is a matrix. But think about the real function. Define, let's say I consider E as open interval 0 1 union, let's say 2 3. So now my function from E to R defined as f of x equals to 1 if x belongs to 0 1. 1 by 2 if x belongs to 2 3. What is the derivative of a function at x point? 0. But the function is not a constant function. Okay. So this gives you the answer that why it is. So it must be a constant function is a false statement. Okay. It must be a constant on a connected component of E. Obviously, it's true. Correct. So if we have an open set, if we have a connected component, it should be like, think about that. D is a subset of E. Now for all points of X, f dash X equals to 0 for all X belongs to G. That means, so now, okay, for connected component means what? So we have a D subset of E, and D is convex. And f dash X equals to 0 for all X belongs to E. Obviously, this will imply that f dash X equals to 0 for all X belongs to D. Because D is convex, so this will imply that f is constant on D. Okay, so yeah, like it's a part connected. So so in the real line, Rn, I think they are same type of thing. Rn it will be, I think they are same connected because it will be part connected. Yeah, that's the problem. Every part will be here.
It need not be convex. Can cover the set E with convex subsets.
But in each convex set, it can be defined up.
And then you allow for intersections, then in the intersection also it will happen.
Like you were saying that you can write the union of intersection of convex sets. Right? Okay, that's yeah, like that's my mistake. For example, if we consider the circle, circle is a connected component, but it is not a convex. But whether we can prove the same thing, no. How can we have circle is convex? Circle is not just a circle, bounded, not inside person. Because any 2 points you can join by a line, so it's a connected thing, but it's not convex. Okay. Then what will happen? Point. So can you find a counter example in that case? That's the question. Can you find a counter example which will be like that? Let's say so consider J. J is a closed set. Okay. So Rn minus J. Okay, we'll see the statement later. But let's go for the next question. If x is 0 or 1 for all x belongs to E, this is not true again. That same example. Open 0 and union 2, 3 is not true. And if of E subset of Z, that is also not true. So actually, all are becoming false if P is not true. So we are correct or we are making some mistake? Okay, we'll see the B later. Okay, question number 39. Verify the following statement. F is differentiable at 0, 0. F is differentiable at 0, 0 and df of 0, 0 is invertible. So, but we don't have to, we have to think about partial derivative. If partial derivative are continuous functions, then the whole function will be differentiable at 0, 0. F is differentiable at 0, 0 and F is. Okay, let's go one by one. What is the component? So I hope that you have this 3x plus 2y. Please tell me. What is the question of 39? 39 or 40? 39. Okay, what is our f1x? 3x plus 4y, 2y plus y square plus mod x square. And f2x is 2x plus 3y plus x square mod x. So we have no problem with other point, but 0, 0 is the problem you are saying. Okay. So can we get the partial derivative of f1 x at the point 0, 0 or not? Okay. So what is the partial derivative of f1 with respect to x at the point 0, 0? The formula is limit h tends to 0, f1 of x plus h. So in this case our will be 0 plus h comma 0, 0, 0 by h. Limit h tends to 0. What is this value? 8. So 3h only. And this value is 0 by h. So we are getting 3. So derivative exists at the point and the value is 3. What about f1 of y at the point 0, 0? Yeah, it will be 2. And del x2 del x at the point 0, 0 will be it's 2 again. Okay. 2 and del x2 del y at the point 0, 0 is. So these are the values we are getting. Check the continuities of the function around at least in the neighborhood of 0, 0. Okay, but you will check that it will be continuous. Okay, so we are not doing it. But check that it will be continuous. But what will be the matrix of F then? The EF of 0, 0 will be. It will be 3, 2 or 2, 3. 3, 2, 2, 3. So 9 minus 4, if you take that, okay, this is okay. And if there is not 0, so invertible. So derivative exists at the point and derivative is also invertible. So it's fine, both statements are correct. It is clear. We calculate the derivative and then.
Suppose if we
assume that if it is not equal to 0, there is a point A where the f of A is not equal to 0, then we can consider the open, like it is an interval, minus infinity to f of A one interval, f of A to infinity other open interval. These two are open set and the differentiability is continuous. So this inverse only will be again open. Now for the connected component, we got two open sets, which will means we are able to divide the connected component with the non-empty to inline open sets. Okay. Means what I am trying to say, suppose we want to prove this is constant.
So suppose you have to prove that it must be constant on a connected component of P.
Okay, if it is not, then for two different times we will get f of A equal to f of A not equal to f of B.
So there will be 2 points where
F of
f of A not equals to f of B. Okay, and this is a connected set. Okay, then
so for f of A is not equal to f of B, we can consider an open interval minus infinity to f of A, f of A to f of B one interval, f of B to infinity other interval. B open interval we got now.
okay.
Since it is R, so f of A, either f of A or f of B will be less than B, one of them is less than or greater.
So now, but when you are proving it, okay, you say E. Oh, okay, R is given.
R is
F is E from R. Okay, that we have to consider.
by these three open interval, we can get the inverse image. That will
Okay, I missed that. I was thinking about in terms of Rn. Okay, so it's an open set. Rn. So we have now. Let's say there are 2 points where the values are different. Now we are considering this open interval minus infinity to f of A. Let's say f of A is less than f of B. So union f of A, f of B, and f of B to this. Okay. So now what is your
now these are open set. If we take the inverse image, that will be open.
yes, that way actually the whole real line you are taking.
Yeah.
So it will be the whole thing.
Yeah, so that each of the inverse will be open. Inverse images will be open. Now for that connected component, if the connected component contains either one of them or all of them, whatever it is, we are able to give it the separation.
No, can't be. I'm not getting separation.
Initially, if you try this way, if the function differs at 2 points, then what you do is you take the largest open ball centered at each of the 2 points, and then you start constructing a path from A to B. So, and then put open intervals. Now, the intersection of 2 open balls should be convex. So you can apply the result again and again, and then you should be able to show that the value of the function is in the open ball containing A, and the value of the function in the open ball containing B should be the same.
Okay, so he is saying that it will be so because you can always find like you have you can put the intersection of convex sets. Correct. You are seeing that it's a countable intersection. Any component can be written as a countable intersection of convex set. You are saying at open ball, say around A and B. I'm not sure whether it will work or not. But is it possible to find a counter example? That's my question. Is it possible to find a counter example where in a component this function is derivative of the function is 0, but the function is not a constant function. So R is the main. If there should be function form, but we cannot say that if this is a continuous differentiable function. Otherwise, we can use the property that if this is a continuous and 0 is a connected set. So inverse image should be connected. that you cannot use for that because excess is also not a continuously control. But still, like that something might be true. I mean, others are yes, true, correct. Others are not true. It cannot be. If it's like a 0, 1 for all x or x, that's also not true. We can have a function like that. Any constant function, f of x equals to 2, will give us something. So obviously not. F of a is subset of j also not true. I think there are some issue. I was actually when I made the question, I was thinking about connected and convex mixed up. So it's actually I want to make convex component. Somehow I mixed up and put connected component. But the question remains whether it will be true for connected components or not. That we have to check it later. I will think about it. Okay. You also think that whether it is true or not. But if you are saying so, but you have to write it down so that everyone can see. Okay, this is.
Constant on a connected component of have open in one connected component
It's not so, then we can say that this result is possible.
one connected component is constant.
Yeah, it will be one connected component. It will be a constant. No, it still can't say because again you have to prove. We only prove the result that if on a convex set, if derivative is 0, the function is a constant.
There exists one connected component.
No, see, let's say that E is set is a connected set. So can we say that derivative of f just x 0, f will be constant? So we prove the result for a convex set. So is it possible to prove the result for a connected set? That's my question. Got it? Because in terms of real line, we are keeping real line that most cases convex and okay. So connected, you can think about that like only singleton point 0 is connected but not convex. Path connected is there, but that we consider that line joining A and B. So can we have? I think. Okay. So look at the proof again. Okay. So think about the proof again. So we have gamma of t defined as AT plus 1 minus PA plus T into P. So we use the state line. But now suppose we have a connected set. So the current Rn means a path connected. So we can join the point A and B by a path. That means a continuous function. So all the things are working. But gamma of t will be 1 or not. Okay, we can define this. Like gamma of, we can have a path where the gamma of 0, path means a continuous function from 0, 1 to A and B. So gamma of 0, let's say A. And gamma of B. So initial point of the path is A, terminal point of the path is B. So I think the proof will work. Can you verify that proof will work again? For if we instead of convex set, we consider a connected set. But now instead of state line joining A and B, we are considering path joining A and B. And because the path joining A and B should be inside of E, so all things are okay. Fine, till now it is fine. It looks like it will work. Path is differentiable or not? It's a continuous function. So, okay, we have to get a smooth path. Whether we can get a smooth path or not, that's the question. Differentiable why? That's a point. Like if you have a corner point type of thing, it will join and join. Piecewise smooth we are getting, but actual thing not getting. So please verify this question again. I mean, proof is not working that way, but whether we can find a counter example or not. That's the question. Okay, question number 40, we'll do it later. We are not doing it. Question number 41, I'll just touch it. it is because of what it is saying, because of it is inverse function theorem. It says that inverse function says that if we have a derivative at a point, if it is invertible, the function will be invertible in some neighborhood of the point A. So that means what? For each point, so question number 41. So what is inverse function theorem says? Says, suppose we have a continuously differentiable okay, if there exists an A such that A plus A is invertible. Okay. Let's say B equals to f of A, then there exists, then A will be invertible in some neighborhood of A and B. So there will exist neighborhood U of B and E of A such that G will be a mapping from U to B and it will be a continuously differentiable mapping and G of f of x equals to x. So that means G will be the inverse of the function x. So what it is called intermediate values theorem is saying, if we can find a function where the derivative is an invertible mapping, then you will always going to find a neighborhood of A and B where you will get the inverse of the function. And that inverse function is continuously differentiable mapping. Now you have your answer. Why you have your answer? Because for each x it is given invertible. So that means you will going to get a function which is inverse of A, and that function is continuously differentiable. So you will know that if we have a mapping whose inverse is a continuous function, then the function is an open mapping. So because of that, A will be an open mapping. So what you prove? So if we have a continuously differentiable function defined on an open set, and if derivative at each point is invertible, then function is an open mapping. So open mapping means it will map open set to an open set. So it will map open subset of E to an open subset of Rn. Okay. So that's the idea. So it's the application of just the corollary of open mapping theorem. So open mapping theorem. So that's the one of the application. Okay, 40 will try. Actually, the set of all. This is another question I did not post. The question is that if you consider the collection of all linear operator of Rn, okay, that will form an open subset of Rn. And that mapping which maps a set A to A inverse. So mapping the function matrix to its inverse, let's say, then it will be a continuous mapping. This will try later. Just using the norm definition of norm, you can find. Okay, that's all from my side. But we have to think question number 38. Little. Any question from online participants? Any question? But think about it. Mike is not. Okay, we'll again meet after 15 minutes.
Can you hear? Not means not at all clear or what?
Yeah, now it's fine.
It's fine.
Yeah.
Okay, but you have to tell me it's consistently or I'm not. Yeah, I'm not sure. Not sure. No?
Okay. Yeah.
Still?
Right.
Okay. We'll quickly do a few of the problems from group theory and then go to ring theory. Because there were some interesting problems there which are not done. Interesting simple ones, you just have to know one factor. So, fifth problem in tutorial set 2. What is Z20 Z29? So what can you say about this? There's a set of homomorphisms from Z20 to Z20. Yes? Right. Just identity stable. Trivial homomorphism. Why? 29 is a prime. Okay.
Image of the generator is
Image of the generator has to be a subgroup. So the only possible subgroups of Z29 are 1, 0 and whole. Can it be onto? Can you have whole means it is, I mean, whole group means it is onto surjective. Can you have a surjective homomorphism from Z20 to Z29? No. The image has to be a proper subgroup. The only proper subgroup of Z29 is the trivial group. So that is the trivial homomorphism. Okay, suppose I change this to Z30. Then now is it possible because 30 is larger than 29, right? So can you have a surjective mapping? Mapping, yes. Homomorphism. Why? No. Why not? Because surjective, what I said earlier is 20. This is only 20 elements. This, whereas the other codomain has 29 elements. So you cannot have a surjective function at all. Now it's not true that you cannot have a surjective function. You can have surjective function. But can it be a homomorphism? Huh? Okay. You can say that the generator of, I mean, you know that the homomorphisms from Zn to anything are in one-to-one correspondence with elements there which have the order dividing this, right? So here, this one, here one has order 30. So wherever it maps, or in other words, if you want a surjective homomorphism, then you have to map to some generator of Z20. That's what you're saying. So you have to map. So I can change it so that that also is good. If you want the image of the homomorphism to be Z29, then f of 1 has to be a generator. F of 1 has to generate Z21. That means F of 1 has to be 1, for example. But is that possible? No, because order, you cannot satisfy the order condition. Okay, I will not elaborate. So just think about it. We already did this yesterday. Fine. Similar, another question, sixth question. S3, what is form of S3, Z3? The more general thing that you can think about is any homomorphism from G to F has a kernel, correct? So one thing is image. So image of F needs to be a subgroup of H. Kernel of F needs to be a normal subgroup of G. Also, G modulo kernel of F needs to be isomorphic to the image. Okay. So in order to get another, yeah. Okay, we come to that later. So in order to get the homomorphism, one necessary condition is that homomorphism must have some kernel, such that when you, so some normal subgroup of S3 must be there. Okay? In S3 you must be able to find some normal subgroup which can act as a kernel, so that when you quotient by that, so you quotient by that, you will get a subgroup of, in this case, Z3. Okay. This must be some subgroup of Z3, which is the image. So is it possible, or like how many can you get? Of course, always. Yeah. So is it possible? What are the normal subgroups of S3? Trivial subgroup, whole subgroup, what else? 1 R square. That is 8. Okay. So for any extent, if you take for n greater than or equal to 5, the normal subgroup lattice of Sn, normal subgroup lattice, not of entire subgroup lattice. The normal subgroup lattice of Sn is a chain. Okay. For n equal to 3 also it is true. Okay. N equal to 3 also it is true. N equal to 4 you get one more. Okay. You get one Klein 4 group. It's something isomorphic to Klein 4 group as a normal subgroup. But that is the only exception. Then of course 1 and 2 are trivial because 1 is trivial group. 2 has only 2 subgroups. Okay, so for S2 you know it's just S1 is itself trivial. So other than those cases, you take these cases, this is what the normal lattice looks like. So this picture should be there in your mind. So now when you look at it, you want to homomorphism from that. What are the possible images? That is the first thing you think about. What can be the possible images of the homomorphs? Whatever. Huh? No, in general. So if you ignore Z3 and say if I have some homomorphism from S3, what can be the images? Huh? Order. Okay, so basically these are the images, correct? So these are the this is the normal subgroup like this. The images possibly are 1. If Sn is the kernel, then 1. So trivial homomorphism. Sn mod A is isomorphic to Z2 or S2, whatever you want, right? Order 2 subgroup. I mean order 2 group. Okay, and S3 itself. Sn, I mean S. Yeah. Sn mod 1 is Sn. So these are the only possible images. Now you have to look for these as subgroups of whatever group you have. In this case, you have Z3. So which of these occur as subgroups of Z3? 1, yes. S3, S2. Not same. So again, this is trivial. Okay, not empty set, trivial. The only possible homomorphism is trivial homomorphism. Yes. We have a homomorphism from group G to group H. We know by isomorphism theorem. So what you do is you take normal subgroups of G, and for every normal subgroup can be the kernel of some homomorphism. That is true. So when trying to find the homomorphism from G to H, you just start by listing. So if suppose N1, N2, that lattice structure is not important for this particular case. Suppose these are all the normal subgroups. Then you start by fixing G mod N1, G mod N2, G mod Nk. These are all isomorph. These are all possibly means the images. So that means you have to check whether this is a subgroup of H. This is a subgroup of H. That is a thought process. Which of these can be subgroups of H? And if it is a subgroup, then definitely there is at least one homomorphism with that discussion. How do you get that? Because you just take that. So take the canonical projection, and if you say that this is a subgroup, that means you have some embedding of this into H. Okay. So then that composition is going to give you a homomorphism whose kernel is that G model. So corresponding to every normal subgroup N of G, such that G model is isomorphic to some subgroup of H, not normal, just a subgroup. There will be a homomorphism, at least one homomorphism. You can ask how many homomorphisms. How many will be there? For a given image, there may be several subgroups isomorphic to that. If you fix that subgroup, and if you fix that N kernel, then how many will be there? Not this one.
Oh, that not.
No, suppose we fix. I'm saying that I'm fixing the kernel as N, and I'm fixing the image as whatever. Some A. Yes. How many homomorphisms are there from F to G which have this as the kernel? How many homomorphisms are there from F to H, G to H, which have this as kernel? This particular N as kernel and this particular K as image. If I fix kernel and image, I will do it. Okay, I'll ask concrete example. I want a homomorphism whose kernel is 0 from Z3 to S3, whose kernel is 0 and the image is AN, R. Okay, A3. So that. So I want 0, 1, 2 homomorphism to 1 R squared. How many are there? So kernel is fixed, image is fixed. How many are there? 2. Why is it 2? Because Z3 has 2 automorphisms. You take any automorphism here. Okay. Take any automorphism from G model. You can insert that in between and get another homomorphism. So the number of homomorphisms with a fixed kernel and image will be number of automorphisms of that. Then you can ask how many different kernels can be there which are basically the same, how many different images can be there which are basically the same, and so on. And then multiply. Okay, fine. Okay, you want to spend too much time on this. So next question, 7. But you understood what you also want. The main approach. The idea is you look at kernel, any normal subgroup that can possibly be a kernel, and then mod by that, quotient by that, there has to be a subgroup of that because that will be the image. So you ask whether there is at least one subgroup or not, isomorphic to this G model. If there is, then you have a homomorphism, at least one. Okay. If not, no. So in this case, the only normal subgroups of S3 are S3, A3, and trivet. So if you take G mod N, that is S3 mod S3, S3 mod S3, S3 mod 1, that you do not S3 only. Okay. These should be images, that means subgroups of Z3. Which of these are subgroups of Z3? This one because it's trivet. This is Z2, no? This is isomorphic to Z3. It cannot be subgroup of Z3. Means whatever labeling it cannot occur. Right? This is S3. Again, it cannot be. Its order itself is large. So therefore, the answer is not. Means this is one. I'm saying. Sorry, did you misunderstand? I'm not saying zero homomorphism set. The homomorphism set is trivial, single digit. Yeah, the number of homomorphisms is one. Question is what are the homomorphisms?
How many norms are there?
No simple method. No. You have to like these are the groups for which you have to know what are the normal subgroups, like symmetric, dihedral, then tricyclic, maybe so on. Some of those cases you have to. S3, SN you have to especially know because only this is all or any other than 4 and 1 and 2. Okay, 4 there's special cases there where even there actually it's a chain. Yeah, even for 4 you get a chain, but with 4 elements, not 3 elements. But for any other SN, it's just 3 elements. Okay, so 7th question. Basically the similar question. If there is a surjective homomorphism from G to H, which of the following can be true? First case G is S5, H is S4. Can there be a surjective homomorphism from S5 to S4? So surjective homomorphism means whatever kernel you take, after quotienting by it, you should get not some subgroup of H, but H itself. Okay, so you want this to be surjective. That means what? G mod kernel F is isomorphic to H itself. So in the first case, G is X5 and H is S4. Again, with already what you know, you can immediately solve it. Is it possible? Can you think of any normal subgroup of S5 such that when you quotient by it, you get S4? What is the order of S4? 24. Order of S5 is, order of S5 you don't need to know. Whatever is the order of S5, you know that the possible quotients of S5 are what? Trivial or Z2 or S2 and S5 itself. Obviously, this cannot be S4, right? So no. Do you understand this? Everyone? Understood? No. The previous argument? We are just repeatedly using isomorphism here. So, again, once again, you have any homomorphism from G to H. We know that Why isomorphism there? This is all. G modulo kernel F must be kernel F must be isomorphic image F. But image F must be a subgroup of H. And kernel F must be a normal subgroup of G. So we'll write it down. To find a homomorphism from G to H. Take n which is normal in G such that D mod n is isomorphic to some subgroup of H, not necessarily normal. This can be anything, need not be normal. Some subgroup of H, that's it. You look for normal subgroups of D such that when you quotient by it, you get something isomorphic to a subgroup of H. Okay. So here we have S5. So now I am asking, can S5 modulo, S5 quotiented by some N, which is normal S5, be isomorphic to S4. Remember that S4 has order 24. And another thing is, the normal subgroups of S5 are only these. That is the fact that we repeatedly using this. That the only normal subgroups of Sn for n greater than or equal to 5 are 1 An or Sn. An is index to subgroup. So Sn mod An is always isomorphic to Z2 means it has order 2. Okay. So the only possible quotients that you can get. So the only possible quotients that you can get are these. S5, Z2 is order 2 group or 1 or trivial. Okay. So then you ask, can any of those be isomorphic to? In this case, you want to surjective. The question asks surjective homomorphism. So can any of these be isomorphic to S4? No. I mean, are any of these isomorphic to S4? No, they are not. That's it. Any other question? Just to check. Subgroup, yes. Not just order, but isomorphic. Yeah, you have 2 or 3 or something, of course, order determines that. But if it's 4, you need to check whether it's cyclic or clinical, like it. Okay, then fine. B is G is S4, H is S2. So now is it possible? Yes. Here that too, yes. So yes. Okay. And it is if and only. If you can find such a normal subgroup, definitely one homomorphism at least in this. Maybe more, one at least in this. In fact, there are in this case there is only one because S2's automorphism group is still there. That's it. But again, if the question was you want to find a homomorphism whose image in some larger Sn is S2, then there will be 7. Because every order 2 element of that larger one will generate a subgroup isomorphic to S2. You can embed into all of this. Any question about this? S5 and Z5. Again, this is all you need. So already you have the answer. If the codomain is not any of these, the answer is no. So S5 and Z5? No. S4 and Z4. Okay. S4. So this you have to know. S4, as I said, is an exception. S4 you have. In S4 you have 1, A4, B4, and S4 is it. Order I change. Obviously, A4 is okay. These are the normal subgroups of S4. Okay. So let's just write the order of the quotient. You don't need to know the exact group because the question is simple. So the order of the quotient is going to be either order of S4, which is 24, or in this case order is 1. In this case order is 2. When you quotient by B4, what do you get? Not the group. What order do you get? Order 6. That's a question of whether that is Z6 or S6. But that doesn't matter here because the question is whether there is surjective homomorphism onto Z4. So do you have order 4 here? No. So answer. Luckily, you don't have to know what the quotient is, whether it's Z6 or. Actually, I don't know whether which one it is. You can write it down to check, but yeah.
Z6. There's 4 to Z6. And in that is 6, 6, 9 years.
Yes.
But then D4 will be X. D4 exactly.
Incline forward. But B4 need not place what? B1. S4 is what whatever subgroup it has isomorphic to it. So it should be isomorphic to Z6. That is the question. Is it? I don't know. So that question probably won't be asked because that requires even more knowledge. Because what exactly is questions? That we don't know. Okay. But you can still, they can, for example, ask. So let's say, I'll change question. Is there a group homomorphism from S4? Not surjective, just group homomorphism from S4 to Z3. Is that? Oh, okay, wait. No. Questions? Only trivial, yeah. That's not a question. Correct. Only trivial possible. So, yeah, you without knowing that exactly, you can't answer it. Fine. So, I think next question is keep order of Z2 square. It's just calculation. You have to automorphism group of Z2 square. Although, do you know the automorphism group of a vector space over a finite field? Your finite field. Vector space over a finite field will be finite dimensional vector space over a finite field will be of the form. So suppose you have a field FP. Then a finite dimensional, n dimensional vector space over this will be isomorphic to FP power n. That basic. What is the basic theorem of? What is it? Vector space. Whatever. I don't know the name of it. But what does it tell you about the dimension and the structure? That if you have n dimensional vector space over F, that vector space is isomorphic to Fn. The vector space of n tuples. That's even true for infinite cardinality. You have a particular infinite cardinality, whether it's countable or uncountable or what. If you have infinite cardinality also, that dimension completely determines the structure. So you can't have two non-isomorphic vector spaces of the same dimension over the same field. All of them are isomorphic to one another. Okay. So that is completely different thing. So if you have, even if you have some other infinite cardinality also, it's still going to be that. Okay. Okay, anyway. So right. So what are the automorphisms of this? Yes. But is it just commuting? You need not commute them. Commuting is a special kind of automorphism. You need not permute the basis elements. You can map some basis to another basis also. Like a basis, you have to map a basis to a basis to get outcomes. But it can be a different basis. So if you fix a basis, you need not permute it. Means even if you fix a basis, you need not permute it within itself. You can map 3 basis elements, for example, to another basis. Okay. So in this particular case, you have Z2 square. So you can think of it as that in the negative part of it is. What are the elements in Z2 square? And also one. So for example, you can take this basis. That will be like this is E8BC, let's say. A multiplication notation would write A B is equal to C. But AC is also equal to B. BC is also equal to A. So any two of these, any two non-zero, non-identity elements generate the group. Or in the vector space here, any two non-zero vectors will form a basis. Okay. So if you fix a basis, then you can get all automorphisms by mapping them to any other basis. So that is a question. If you take ABC, so I'm writing the vector space thing because you can generalize it to this case. Then you get a nice answer for number of, you get the exact number of automorphisms. That's a nice answer for it. Work it out later. But in this case, let's say you fix the basis as AB. Now you can map these to okay, so you can map these to ABC injectively. Every such mapping is an automorphism, means defines an automorphism. That's all. We already know homomorphisms are one-to-one correspondence with those things. So here automorphisms means you need this is a generating set of the group. The image of the generating set under the mapping that you define should be a generating set. That's it. Okay. And any mapping will work because the relations will automatically be satisfied. As long as it's injected, it will. Okay. So what all possible are how many injective mapping? Question is now how many injective mappings are there from AB to ABC and what group does it generate? Yes, 6. There are 6. You can map AB to AB or BA or AC or CA, BC, C. Okay. What group is this? Is it Z6 or S6? I mean S3. So you have 6 automorphisms. That forms a group also in a group of order 6. But is it commutative or not? Okay, if you write it down in commutation form, you take ABC and yeah, so it's not a permutation of one basis, but you can say what are all the possible, in this case, if you write ABC, right, it's a permutation of ABC. ABC is not a basis. AB is a basis, a BC or AC. But it is a permutation of ABC because that's the only thing you can do. So if you fix A and B each, then you have to fix C. Whereas if you interchange them, then again you have to fix C. Okay. This should already tell you what it is. Then you can map A to C. But if you map A to C, where does C go? A to C and B is fixed. B is fixed. Then where does C go? C has to go to it. and so on. So what will you get? You will get all the elements of S3. So automorphism group of Z2 square is isomorphic to S3. Okay. So it is not a B. That's the question is not B. So if I have a generating set for a group G, to get an automorphism of G, okay, I need to map E1 GK to some other generating set of G. Need not be the same generating set in permutation. Can be any other generating set, but it has to be an injective mapping because it's an automorphism. So I will definitely get K generators. So I have to find some other generating set. I mean, some generating set with K elements in some order and map. And every such mapping will give me, provided the order conditions satisfied and whatever other relations are there, they are satisfied. Here we don't have to worry about that. All the elements are the same order too. Okay, it's a prime element, and they all satisfy the same relation. Any two, when you multiply, you get the third. That's it. Okay. So yeah. So here the automorphisms of Z2 square, that means prime for Z2 square is prime for group. That's why I'm writing EABC. Are in one-to-one correspondence with injections from AB to ABC. Okay. Set of injections from AB to ABC. Why? Because AB is, you fix one generating set. You don't have to change this also. Then you will overcome. Fix a generating set because that has to go to something under homomorphism. That's it. So fix that. Then see where all can I send it. I can send it to A and B respectively, or A and C, or B and C, and so on, like that, or B and A. That order also matters. That's a different function. So that's it. Okay. Okay, next question you already know how to do because we have done the theorem. Order of HK, as I said, is order of H, order of K divided by, cardinality of HK set is order of H times order of K divided by order of H into K. So you just have to see what are the possibilities. The answer is 60, right? Because H and K both have order 12. So 12 times 12 by something cannot be 60, because 60 has 5 as a prime beta set, 12 does not, so can't. Then, is there a non-trivial group homomorphism from C to R? Is there a non-trivial group homomorphism from additive group of complex numbers to additive group of real numbers? Yes. So if you are saying that, for example, this mapping that maps Z to real set, it's a group homomorphism. Yes. Yeah, that is true. This is a group homomorphism, correct? C to R, yeah, correct. This is a group homomorphism from C to R because the only thing we need to preserve is addition. Real part of Z1 plus Z2 is real part of Z1 plus real part of Z2. Okay. Yes. Next question, more related. Which of the following pairs of groups are isomorphic? First one, R and C. What do you think? Okay, first let me ask. R and Q. Are they isomorphic as groups? Why not? Yeah, they are not even isomorphic as sets. There is no bijection from R to Q. Right. So of course not. This is real. R and C are both uncountable. So you can't dispose of it directly. I already said what is required for, like earlier in something else I mentioned what is required for this reason.
There are two elements in satisfies three elements in satisfies is by equals P.
This is additive group. R and C. Additive group. You are answering second part. Yes, second part of the previously, in some other context, I mentioned something which is useful for us. So actually, you have to go outside group theory and do something. To elevate this problem to some other stronger structure, a bigger structure. Yes? As vector spaces. Are they isomorphic? Why not? As vector spaces over what field?
Dimension.
Okay, but that does not help. Because if you make it a, that's what, if you cannot say no by finding some particular construction which adds structure to this and then say those structures are not isomorphic. Maybe they are isomorphic as groups. It is like as sets are they isomorphic? As sets. But they are both uncountable, same uncountable cardinality. They are. So if I am trying to prove that they are not isomorphic as sets, and I say okay as groups they are not isomorphic, therefore as that is wrong. So no, that case. Only if you want to say yes, you can. So in fact, I want to say yes. They are surprisingly they are isomorphic. Yes. Although they don't look like they are isomorphic. Yes. So R over R and C over R are not isomorphic as vector spaces. What other field can be? R over C you can't take. So what else? R over R and C over R are not. And if it's R over R and C over C, there is no question of isomorphism because there is no notion of linear transformation between vector space over different fields. What other common field can you take over which both of them form it? R over R and C over Q. What are the dimensions? What is it? Uncountably. Both are uncountably infinite, I mean of uncountably infinite dimension. So by the theorem I mentioned previously, they are isomorphic as vector spaces. Any two vector spaces of the same dimension, whether it's finite or infinite, over the same field are isomorphic. So they are isomorphic as vector spaces. But for vector space isomorphism, first of all, we need group isomorphism. As additive, the B plus has to be isomorphic to W plus. Okay. So yes, they are isomorphic. But if you ask what is the isomorphism, we don't have this. There is no construction which will give you the isomorphism from group R plus to group C plus. So it is a non-constructive.
Say that two vector spaces of infinite, same infinite dimensions are isomorphic.
There is a non-constructive proof. For the finite case, we can do it by taking the basis. For the infinite case, there is only non-constructive proof. I'm not sure I remember how it was. Probably axiom of choice. Yeah, you require axiom of choice. Okay, so that itself makes it definitely non-constructive. Yeah, you have to choose using axiom of choice. So you can't actually do it. If you could actually do it, then you don't need axiom of choice. So okay, R star and C star. That is a multiplicative product of non-zero variables and non-zero complex numbers. Are they isomorphic? No, because that's what you were saying.
Only two elements. It's my a square equals to 1.
Okay.
Okay, or 4 is equals to 1 R. But in C, there are 4 elements.
Yes. So in C, there are 4 elements. 1 minus 1 minus 1, I minus I, which are 4 roots of unity. In R, there are only 2 roots. Okay. Or another way to say it is what are the finite subgroups of R star? How many finite subgroups are there in R star? R star multiplication. 1 comma minus 1 and 0. That's it. Means trivial and 1 comma minus. That's all. Just. Oh yeah, not 0. Sorry. Yeah, correct. 1 and 1 comma minus. Just 2. Okay. Whereas in C, how many are there? Infinitely. You take any nth roots of unity. That's something. Right? And in fact, there are so many other things that are. Okay. Moving on. S3 cross Z4 and S4 are they isomorphic? In order the same, right? S3 cross Z4. We didn't direct this one direct products. Okay, we'll certainly calculate. S3 cross 4. So, any idea based on what we saw previously? Do you have anything using homomorphism? Sorry. What order same? Huh?
No.
Okay, that's one thing. You can use a number of. Okay. But using what you already saw before. Okay, subgroups. Normal subgroups. So normal subgroups of S4 are 1, B4, S4, A4 and S4. These are the only normal subgroups here. Clear? Okay, yeah. So that's what you're seeing. Order of element, yes. In S4, there is no element of order 6. How? What is the order of permutation? I mean, in terms of the cycle decomposition, if you know the permutation, yeah, it's the LCM of the cycle lengths. So in S4, you have only 4 points on which you can permute. So whatever cycle you construct, the cycle lengths can be. Anyway, can you get 3 and 2? That is the question. Can you get 6? Of course not. Can you get 3 and 2? No. So then you can't. Whereas S3 has S3 in S3 you have. What did you say? S3.
In the
In S3 cross Z4. Yes. What is that? You can take 1, 2, 3. And order 2 element, which is 2. Okay. So add on addition on the second component and multiplication of this component. Yeah, composition of this component. Yeah, so this is one way. Another way which I easily see it. You have G cross H. What are the guaranteed normal subgroups of G cross H? Yes, so specifically? Yeah, G cross 1, G. G and H are both normal subgroups of G cross H. And yeah, any normal subgroup of any one component, more generally, any normal subgroup of G cross any normal subgroup of H will be normal. Okay? But there can be more. There may be more, but I'm not saying this is exhaustive. There may be more normal subgroups other than ones of this kind, but these are definitely. So in particular, yes, G and H. So S3 is a normal subgroup of S3 cross Z4. Is it a normal subgroup of S4? No. Is Z4 a normal subgroup of S4? No. So Z2 square and Z4, you know the answer. Huh? No, B4 is B4. But yeah, so this is simpler argument definitely, which doesn't use that fact. You have to know this. And I know that. So Z2 square and Z4, 4 square. Definitely not a universe. Okay, let me see if any. The proper subgroups of R is not an easy question, so I will not take that up. But I'll tell you that. What are the proper subgroups of R? I mean, you don't even have a very nice answer. I can tell you what they are. They are either cyclic. First of all, either zero or okay, cyclic is also there. They are either cyclic. Infinite cyclic, okay? Infinite cyclic groups or zero, or they are dense. So that requires a bit of proof, okay, which we want. So or they are dense enough. So these are can't classify them. Yeah, I don't know classification. I don't know if there is a classification. What exactly there, but they are dense. But these are the only possibilities. Infinitely. Because this is infinitely many. You can take any element and generate a subgroup. Cyclic subgroup. So uncountably many. Next question is interesting. True or distrue? If G is infinite, so is SL of G. That means any infinite group must have infinitely many subgroups. Is that true? Subgroup, infinitely many subgroups. That's it. Must have has, I didn't say infinitely many finite subgroups. Infinitely many subgroups. Yes. Every element. So G is an infinite group. Every element of G generates a cyclic subgroup. Okay, does that close the matter or something else? Yeah. Maybe there are only finite, many different elements may generate the same. What will you? Okay. How many subgroups does Z have? Infinitely many. So suppose X is of infinite order. You take X. There are two possibilities. X can be isomorphic to Z. That means X has infinite order. Then its subgroups are only infinite. So G has an. Okay. So this has infinitely many subgroups, which are subgroups of the original group. So that if every X has finite order, then what? If every X is finite order, then they can't all be same. Means then you must have infinitely many distinct ones because you take finite union of finitely many of those. You will only get finite set. You will not get whole G. So there must be infinitely many. So if not, or if it is periodic, means if not means G is periodic. So since G is contained in the meaning of this, this must be infinite number. Okay. So this is infinite. Right. The answer is part of the next question also. Okay, we'll move to 7 minutes. We'll go to actually I think only 5:50.
Okay. So please wait 2 minutes. I will take 2 more minutes. I will discuss the solution of them.
Okay, then I will stop.
No, sir. Okay.
Huh?
Wait. I mean, 5:50 is.
Oh, actually 5:50. It's okay. You do this correct.
Take 2 minutes. That question, there you only have to spend time can say. Easy, basically, I mean that point. So, like, if we have is an open connected subset of Rn, and you have a continuously differentiable mapping from E to Rn, such that if just x equals to 0, then it will imply that f is constant. So how will we do it? Let's take a point x belongs to E. Now consider this state A, all x belongs to E, such that actually x is fixed with it. Let's fix it and we consider Z belongs to E such that f of z equals to k, where your k is nothing but f of x. Since f is a continuous function, this is a closed set. So A is closed in E. We'll show that A is open in E. So let's take a point Z belongs to A. So now, because Z is also in E and E is an open set, so there will exist a ball containing J will be, so then there exists a ball, say BAR will be inside of E. It will be subset of E. Now, because it's a convex set and if the x is 0, so f will be constant over here. That means what? F of z, so for all W belongs to BAR, f of W will be equals to f of z, which is nothing but k, because this is convex. That means what? This ball is inside of it. This implies ball is inside of A. So this proves that A is an integral point of A. So A is an open set. So A is a non-empty, open, closed-open set, open connected set space, which is not possible, and it's non-empty. It should be the space itself. Okay. Therefore, A is no longer. That means all the value it is a constant. Yeah, that this is convex. So therefore, it does W is same as A, the constant. So this is the one way I was thinking. And first, initially, I was thinking in terms of that group. So in that group, I'm not sure. I'm not sure about the result, but it looks like if we have a path, you can always approximate that path by a sequence of piecewise smooth path. Now, for each piecewise smooth, so you are joining A and B by piecewise smooth path. Now, for each corner point, you have this derivative will be that difference of two corners. Then, if you take the sum, it will be nothing but the end points, sum of these two end points. So, I think that is another way we can approach that same by using the group of numbers. If it is directly using the property of connected set. Try that way as well. Like, I'm not sure about the result, of course, but maybe in smooth manifold, this is so. That means in Rn it will work. Like any path can be approximated by a sequence of smoothwise. But I mean, at least like you can add the smoothwise path and you can approximate the whole thing. Small n, right?
Oh, small and simple.
Oh, sorry. Small. You need to say small. The ball center actually. will be inside of because he is an open. Okay, I will not take it. Now we have the answer. That option B correct. B or C. B like. Can I continue? I think.
Do you want ring theory? Huh? Sure. Okay. Just 15 minutes, okay. You have already seen the sorry? These questions only. Group questions over, no?
They're on.
Okay, let me see what is the meaning. Okay, good. Fine. 3 minutes I'll finish it. Yeah, 13 questions over. So 14 question. Which are the following can occur? G is finite. Number of subgroups G is infinite. Of course, not possible, right? Power set of G is only finite. So subgroups are subset. So not possible. G is infinite, but SL of G is finite. Is that possible? Just now we proved not. G is infinite, SL of G is also infinite. We proved that just now. Then G is countable, but SL of G is uncountable. Is that possible? G is countable, SL of G is uncountable. Okay, before that, part D. G is uncountable, but SL of G is countable. That is, G is an uncountably infinite group, but the subgroups are countable in number. Is it possible? The proof that we gave just now for this. Basically, the same argument we tell you that it cannot, because here again, whatever cyclic group you get, every element will generate, okay, that's it. Every element will generate a cyclic group, which is at most countably infinite. Finite or countable. So countable. Okay, I'll just say countable for finite or countable. So every element will generate a countable cyclic subgroup. Cyclic means countable. So can their union be G? I mean, not like that. Yeah, there are uncountably many of them. No? The question is how many of them can be? Right. Again, that list must be uncountably infinite because you must have an uncountably many distinct countable sets to make the union uncountable. If you have only countably many cyclic subgroups, that union will be countable, so it cannot be the whole thing. The same argument, basically the same argument, but using the countable versus uncountable rather than finite versus infinite. Okay. So yeah, the same thing works there also for part D. It says that uncountable group must have uncountably many subgroups. Part D. Yes. No. There's so many subgroups, but finite subgroups only. Like, who will generate a subgroup? No. What is that? That is also subgroup, but it's not finite. It's an infinite cyclic group. So all the other elements, other than 1 minus 1, all the other elements will generate infinite cyclic subgroups. But cyclic subgroup is always countable. In fact, any finitely generated subgroup is countable. Okay, finitely generated group is countable always. So you list all the cyclic subgroups. Uncountably many of them are there in the list. But when you make it a set, will it become countable? No, because then their union, the countable union of countable sets cannot be uncountable. Therefore, you must have uncountably many distinct elements then. That's it. Yeah. So C, part C is the question. Can you give an example of a group that is countable, but its number of subgroups is uncountable? Is that possible? Finite group with infinitely many subgroups, not possible, clearly. countable group with uncountably many subgroups, is it possible? Q is an answer, correct. But how will you prove it? Proof is a bit difficult, but Q is an answer. Yes, Q is countable, but it has really many subgroups. Okay, I think you have to argue using density, not density.
Perhaps in good picture, power set of.
Yeah, basically, if you take similarly, right? If you take any. Oh, okay, it's something. I'll tell you the rough intuition for this. You take a prime T, okay, and leaving that prime, you take elements with denominator. So you take elements with denominator not divisible by P. Yeah, and generate the subgroup. In fact, not a particular prime. You take a set phi of friends. You take any set phi, finite or infinite, you take any set phi of friends. And you take elements which don't have any of the elements. So this is a set of things. You take elements, or rational numbers whose denominators are not multiples of any elements of pi, any elements in pi, and generate a subgroup with them. Can they contain any element which has a denominator in the set, or denominator whose multiple is this? No, because when you add rational numbers, the denominator will always be multiples only, right? So you can never get any multiple of this in that subgroup. Okay. How many subsets are there? Uncountably many, because it's any subset of prime numbers. Infinite also. So uncountably many are there. They are all distinct. Whatever set you take, they are all distinct. So that's one way. Another answer is to take set of all finite. How do I write it? Just like okay. Set of all finite subsets of n under symmetric difference operation. Since you take only finite subsets, there will be countable infinity, right? Set of all finite subsets of n is countable. That you have to think about like this. So that is countable. But now you take any set S, any subset S, including infinite subsets, any subset S of n, and then take again set of all finite subsets of S. Take set S which is infinite, but take only finite subsets of S. This is going to be a subgroup of this. Correct. Basically, any power set you take will be a subset because the operation is delta, symmetric difference. It will be closed under. If you take any whatever power set you take, it will be okay. As long as it's a subset of. So this is definitely a subset of this. It is definitely a subset. Okay. So how many of them are there? Uncountably many, because I'm taking all subsets, not only finite and infinite. So there are infinitely many of them. Are they all distinct? Yeah. If you take two different sets, SLP, which are not the same, then this will contain some S and this will contain some T. Neither of which is the other. Then one of the elements in this is singleton S. One of the elements in this is singleton T. This cannot be in that. Okay, this cannot be P fine of T. This cannot be P fine of S. So definitely there is. So you have definitely many, incountably many distinct circuits. Okay, okay. Think about the argument again because I want to. And 15.1 is the following number. What Z is isomorphic to Z? Is it true? What Z is actually isomorphic? Okay. Second question is also there. which of them is true. Odd Z is actually this. Yeah, second one is true. There are only two automorphisms for Z, either identity or invariant. Either you fix it or you rotate it 180 degrees. Means have 1 to minus 1, minus 1 to 1, and so on. Okay, so n to minus n. That is the only other thing. Okay. Think about why that is. If G is cyclic, then odd G is cyclic. Is that true? G is cyclic, automorphism group of G is cyclic. Okay, firstly, what is automorphism group of? So for Z, it is true. Odd Z is Z. That is true. So what are the other cyclic subgroups and other cyclic groups? Zn. What is odd Zn? Again, you know the homomorphisms from Zn to anything. So homomorphisms from Zn to Zn are in one-to-one correspondence with elements of Zn. Because any element of Zn will satisfy the order condition. So any homomorphism, any endomorphism of Zn, okay, will be obtained by mapping 1 to some k. Okay? To any k. And whatever k you take, it will work for endomorphism. But which of them will be automorphic? Yes, this k will have to have the same order because it should be a generator. One is generator, k has to be generator. K is generator if and only if it is co. So this will in fact be isomorphic to the group of units of Zn. Okay. So the question is that group cyclic or not for every n? For every n, is Zn cross cyclic? What is Z8? What is group of units of Z8? 0.357. The simplest representation of, simplest concrete realization of which group? Klein's group, V4. Simplest concrete realization of V4. Okay, Klein's group. If 1, B square, 5 square, 7 square, 1. So that is not true. C is not true. If odd G is cyclic, then G is cyclic. Is that true? Odd G is cyclic, then G is cyclic. Something we discussed tells you that. I give you two. If odd G is cyclic, implies every subgroup of odd G is cyclic. What is the guaranteed subgroup of odd G other than trivial and itself? No, not this. No, I mean in general. In general, for an automorphism group, what is one subgroup that you do? Inner automorphism. So this is also there. But inner automorphism group is isomorphic to is all that. Isomorphic to G over Z of G. So G over Z of G is cyclic, then G is a V. Okay. So okay. This is question is whether it's cyclic. Wait, did I repeat the question? No, it's only once. Yeah. Okay. Yeah. That is converse. G is cyclic and not G is cyclic. Okay. So you know that G is abelian. And then inner automorphism group is trivial. I think I went to ask again, but okay. Cyclic, fine. Group of Oh no, then you have to use the fact that G is abelian. Yeah, you have to use the fact that G is abelian. If G is abelian, what can you say about its own? Finitely generated is not good. Okay, let me think about this later. No. Part E. If odd G is trivial, then G is trivial. Is that true? Odd G is trivial, G is trivial. Carefully. Huh? Z2 also has trivial. Z2 also has trivial automorphism. Because there is only one non-invariant element in Z2. Correct. One has to go to one, then two has to go to two. Two cannot go to one because it's injected. So two has to be second element, 0 and 1. So 0 has to go to 0, 1 has to go to 1. So that is not true. Okay? But it's almost true as the next problem shows. If G has order greater than 2, then odd G is non-trivial. Yeah, okay. Right. So also there are cases in this book. Okay, what is one guaranteed way to get automorphisms? That is if you are abelian. Okay, so if you map X to X inverse, that is an automorphism if G is abelian. Okay, so G is abelian. So actually there are three cases. Okay. So X going to X inverse is an automorphism if G is abelian. G is an abelian group. This is an automorphism. There is one more case, no? Yes, you said conjugation. Yes. If G is non-abelian, then that's you know that inner automorphism group is non-trivial. That's all. Inner automorphism group is non-trivial. So automorphism group is non-trivial. Okay. In this case, is it non-trivial or this? X going to X inverse. X is involution. Involution. That's what I did. Involution. I put it on this. So if order of X is not 2, then this is not trivial. Okay. Suppose order X is equal to 2 for some X. Then you're done. No? For all X in G. Actually, you say okay. I think exceptions is already okay. Suppose the order of X is at most 2 for all X. Then you have to know some here. Since every element is self-inverse, then what can you say about G? It is abelian, but what more? It's a vector space over Z. Okay. Then, in fact, you can just say G is isomorphic to Z2 power some omega. Finite or infinite, I don't know. So Z2 power some omega. In which case, it definitely has non-trivial automorphism because you can permute the base elements or map the base elements to something else. Okay, so in this case also, it's not real. Yeah, okay, stop. Hmm.
Maybe tomorrow, most classes will be compulsory. If you get time, then
Huh?
I think I will get finish before then.
Okay.
Okay. But till at least.
Okay, so tomorrow most probably all the sessions will be topology. Okay, and then Saturday definitely only category theory. Okay. Yes.